Hello, everyone. Welcome to another episode going through chapters of A New Kind of Science. This book is about to be 20 years old, and we've been going through one chapter per week, talking about what's here and what's happened since this book was published nearly 20 years ago. And today we are going to cover chapter 9. And in the kind of chapter 9 is entitled Fundamental Physics. Chapter 9 it's a chapter where people who know the book well it's probably one of the most mentioned by its chapter number chapters in the book. Chapter 9 and chapter 12 are probably the most mentioned by their chapter number chapters. Chapter 9 was part of the sequence of chapters talking about the applications of this concept, this new kind of science concept of exploring the computational universe. And the concept in this case was to apply that idea to fundamental physics. And as far as I was concerned, I got a certain distance. This was a seed. That seed I expected would be grown by other people over the course of years. In fact, after A New Kind of Science, the book was published in 2002, I worked a bit on fundamental physics. There was so little enthusiasm in the physics community at that time, and I viewed that as being the primary audience, that essentially I decided to work on other projects and didn't pursue it. As it's turned out, nearly 20 years later, in 2019, I restarted this initiative to do fundamental physics using the basic ideas of A New Kind of Science. And I'm happy to say, as many of you know, the results were completely spectacular. The seed of all those ideas was in NKS, in the book, but a bunch of new ideas were needed. Some ideas I had, some ideas were brought in by the young folks, particularly Jonathan Gorard, Max Piskanoff, who helped restart this project in 2019. So what's in chapter 9 is a whole bunch of good and interesting stuff. And then but it's an unfinished story. That story has been restarted. There's much to say. And like many parts of the NKS book, what was in some cases almost a footnote in the back of the book has blossomed into a kind of a giant discussion now. So I'm going to talk about what's in chapter 9, and I'll talk a little bit about how it relates to what we now know in the physics project. And I will say that some of the things that I viewed as being blocking items in chapter 9, now that we understand a lot more about the physics project, they shouldn't have been blocking items. I missed things 20 years ago, 25 years ago, when I was working on chapter 9. I missed things which now, in the light of everything we understand today, would not have been blocking items and should have allowed forward progress. All right. Well, with that, let me go in and actually start showing you some parts of chapter 9. Okay, so here we go. So last time we talked about this kind of implications for everyday systems. We talked about sort of everyday physics, biology, etc. Now we're going to dive in to talk about fundamental physics. And the chapter kind of opens by talking about, does it even make sense to use simple programs to study fundamental physics? That's a thing which my friends in fundamental physics, at least 20 years ago, were like, oh, we don't need simple programs. We have string theory. String theory is going to bring it all home. Of course, it didn't. And in the end, I think string theory is probably something that is a kind of a limit of some things that you can see from our underlying models, and that's quite interesting. But that didn't work that way at that time. So as I say here, so it could be that with fundamental, and so it could be with fundamental physics that we've talked about the fact that in previous chapters we've seen that complicated phenomena in sort of the everyday world turn out to arise from simple programs with simple rules. And so it could be with fundamental physics. Underneath the laws of physics as we know them today, it could be that there lies a very simple program from which all the known laws and ultimately all the complexity we see in the universe emerges. To suppose that our universe is in essence just a simple program is certainly a bold hypothesis. I say in the second part of the chapter, I describe some significant progress that I've made in investigating this hypothesis and working out the details of what kinds of simple programs might be involved. But there is still some distance to go. From what I've found so far, I'm extremely optimistic that by using the ideas in the book, the most fundamental problem of physics and one of the ultimate problems of science may finally be within sight of being solved. Turned out it took another 20 years, and it turned out it took me actually taking the next steps to turn that statement into to fruition. But the vector was correct. So let's talk about what that vector was. All right. The first thing that I talk about here is actually not about the emergence of things like space-time and quantum mechanics and so on from simple programs, but rather the emergence of another piece of fundamental physics, statistical mechanics, and particularly the second law of thermodynamics from these things. And as a personal matter, the sort of first piece of really fundamental physics that I got really interested in back in 1972 when I was 12 years old was precisely this problem of the second law of thermodynamics, the law of entropy increase, and so on. And in fact, I showed earlier in the NKS book, I showed the sort of the book cover that really got me interested in that. Where is it? It is in, maybe it's in chapter 1. That really got me interested. There it is. That really got me interested in this question of how could a system with sort of a simple setup, like a bunch of balls bouncing around in a box, how could that lead to increasing randomness, complexity, entropy, etc. So in chapter 9, I start talking about that. And that's kind of the first piece of fundamental physics in chapter 9 is about that kind of thing. But I have sort of a meta model, an idealization of that. And one of the critical features is that the law of entropy increase, the second law of thermodynamics, its story is you go from the simple to the random and complicated. But there's sort of one of the obvious mysteries about that is the laws of physics are in a sense reversible. They're not precisely time reversal invariant, but they are reversible in the sense that there's one initial condition leads to one final state. So you can always go back uniquely from the final state to the initial state. And generally, in the kinds of systems that I've looked at in the NKS book, that isn't the case. In general, there isn't reversibility of that kind. So the first section here just talks about what does it take to get reversibility. Here's something where you can plainly see that given a particular state here, you can always go back to find the previous state just as you can find the next state. Here, all roads lead to uniform black results. And so you can't go back and uniquely deduce. By the time you're at this state where everything is black, you've reached that attractor that everything has been pulled to, which is the all black state. You can't go back and deduce, well, what was the initial condition here? So this section is about when can you make reversibility in cellular automata. And among the cellular automata with two colors and nearest neighbors, what I call the elementary cellular automata, there are a limited number that all have rather simple behavior that are reversible. And you can kind of plainly see why this is reversible. It's just shifting things and you can shift them back as well. Okay, but it turns out that if you look at three-color cellular automata with nearest neighbor rules, there are whatever it is, 7 quadrillion, is that right, of those rules. And I went through and figured out that 1,800 of those rules are reversible. And here are some pictures of what those reversible rules do. So you might have said, oh, if the system is reversible, its behavior will be somehow trivial. That's not the case. The behavior is still capable of being perfectly complicated. The force of this phenomenon, which ultimately is encapsulated in the principle of computational equivalence, the force of complexity, so to speak, is certainly far too great than to be held back by just the requirement of reversibility. Okay, so this is an example of a particular way to make a reversible cellular automaton. Here we've got just 3 cells making a new cell, but with a preceding cell also taken into account. So it's kind of, this picture is sort of, the rule itself immediately is reversible by virtue of the fact that the new color of the cell is the XOR, the sum mod 2, of the color that you would deduce from this, from applying just an elementary cellular automaton rule to these triple of cells, together with the color that you had of the cell on the previous step. So it's kind of like in differential equations, when you have a first order equation, you might have something which is not time reversal, which doesn't have this reversibility, but by the time you have a second order equation, you can kind of set it up to be immediately reversible. So you see here, we've started off from in the middle here, we have a very simple initial condition. When we go forwards in time, we get sort of complicated behavior. And when we go backwards in time, we also get complicated behavior. And it's reversible, so we can see that what happens forwards is the same as what happens backwards. But the fact that it's reversible has not prevented it from making complexity as we go forwards, even from that simple initial condition, or its simple condition. Okay, so now we can look at lots of different rules. I've called them things like rule 90R for reversible, with this kind of trick of using XOR, the mod 2 trick there. And we can see these different kinds of behaviors that we get. So these are all elementary cellular automata. There's rule 30, starting off from a single cell initial condition. Rule 30 in its reversible form actually turns out to be rather trivial. It isn't so trivial when you look at it with an arbitrary initial condition. But so this is, again, given reversibility, it's adding reversibility. So this is asking the question, how does reversibility affect the overall behavior of systems? And the answer is, this sort of general phenomenon of complicated behavior from simple rules is absolutely not affected. In detail, there's an effect. And so these are examples of cellular automata with a variety of reversible rules. Okay, and sometimes this is an example of a reversible class 4 rule, where rule 37 is actually rather a simple rule in its behavior, in its non-reversible form, but in its reversible form, you see it's producing all these structures. It's producing the same kind of structures that we've seen in things like rule 110 and the other class 4 cellular automata. Okay, so that's going to be important when we talk about thermodynamics in a few minutes. Okay, so let's talk about thermodynamics, the second law of thermodynamics. What does the second law say? The second law says, if you prepare something in a simple initial condition, with a simple initial condition, then which you can say that then it will tend to become more random. And we characterize that by talking about entropy. What is entropy? Entropy is, well, there's a logarithm in there, but it's basically the number of states consistent with some constraint you put on a system. So, for example, if you're an observer who can tell what the color of every single cell is, then what's going to happen is there's just one configuration of this system that you can always tell that you have a particular configuration of this system. But if, on the other hand, you're an observer where all you can tell is what's the total number of black cells, what's the total number of white cells, then there are many states of the system that will be consistent with some particular conclusion about some particular statement about those parameters. And so the idea is that, as a practical matter, when we talk about the entropy of systems, what we say is, with the coarse graining, with the kind of way that we're observing the system, this is the number of states of the system consistent with our way of observing the system. There might only be, if we knew every detail of the position of every molecule and so on, we might be able to know the particular state of the system. But what we're saying is, at the level of observation of the system that we are making, there are this number of states of the system consistent with that observation. So, for example, if we put the number of black cells in bins, and we say how many black cells are there in this spatial region, that spatial region, and so on, in this case, we would conclude that what we have is something rather special, because we've only got black cells in a particular spatial region here. But if we do the same thing over here, we say, well, actually, this looks quite random. There's black cells in every spatial region, sort of the number that we expect, and so on. And so we would tend to conclude that this is sort of a maximum entropy state, a state where every possible thing is consistent with the observations that we make. And so that's sort of the story of the second law, is that we tend to go from untypical initial states to much more typical, according to our schemes of measurement, final states. So here's an example of that happening. We go here from this initial state, and we're sort of gradually, we can think of this as sort of particles bouncing around in a box, and they gradually get more and more random. And then we have these kinds of structures here. Now, eventually, if this is a finite system, there will be what in statistical mechanics is usually called Poincare recurrence. Eventually, because there are only a finite number of states and the evolution is deterministic, after that number of states, which might be exponential in the size of the region, that number of states, eventually the system will repeat. But it might take an exponentially long time. And realistically, with this number of cells, we'll be waiting, the lifetime of the universe or something for the thing to actually repeat. So as a practical matter, what matters is how quickly, whether the thing sort of goes to a state where it seems typical of all possible states, and whether that happens quickly. And in this case, we can see that it does. Okay, so what about reversibility? Well, this is an example of reversibility in action. Yes, we start from that simple initial state, which we can describe with our various coarse graining procedures as being untypical of the ensemble of all possible states, having low entropy, and it evolves to something which is typical of all states and has what we can consider to be high coarse-grained entropy. But now we can say, well, what about reversing the thing? Is this reversible? Well, yes, it is. If we go backwards, we see exactly the same thing happening. So in a sense, we've prepared this very special state where we're in this special kind of low entropy, not consistent with just purely random behavior state, which going forwards in time becomes sort of randomized, and going backwards in time becomes randomized. And that's kind of the story of what happens in physical systems when we think about the second law of thermodynamics. What's happening is that we are somehow preparing a state that's somehow special. And the big point about the second law of thermodynamics is it says whether we go forwards in time or backwards in time from that state, we will tend to get something that is increasingly random. And it's been quite confusing to people how that possibly works. I think finally with the ideas in NKS, we finally understand something about how that works. Okay, this is an example to just sort of bring home the fact that this really is related to what happens in statistical mechanics of gases and things like this. This is an idealized gas. I'd kind of forgotten this page, actually. This is an idealized gas where you have a bunch of discrete particles on a discrete grid, like a simplified version of that model of fluid flow that I had in chapter 8. What one's doing here is saying with actual sort of realistic or somewhat realistic particles on this grid bouncing around, what can we say about whether one would go from the simple initial condition to the more random initial condition? This is showing that in this case, things are somehow symmetrical enough that the recurrence time is very short and you don't kind of see the thing tending to randomize. But in this case, adding just this extra obstruction, I think it is here, to these particles bouncing around, you do get this kind of randomization of the sort that we expect in the typical operation of the second law of thermodynamics. That's just showing the time histories of those two cases where there's very symmetrical, no obstructions, and this kind of recurs very frequently. In this case, this is the slice taken in the sort of mid-plane as a space-time slice. And what you see here is kind of the analog of what we saw in those just pure sort of made-up one-dimensional cellular automata. We're seeing here from this sort of more or less hard sphere gas idealized model, we're seeing the same phenomenon. You start from a simple initial condition and the thing tends to randomize with time. And this is showing if you actually put a kind of a paddle in the middle of that box and you kind of said, how is that kicked by the particles going on either side? What you see is that in the case where it's very symmetrical, there's this very sort of regular pattern of kicking. In the place where you have this tendency towards randomization, you have indeed a kind of random sequence of forces on that measurement probe. Okay, so let's take a look here. So this is now measuring the actual entropy, as in where the entropy is taken by looking at boxes and saying, given some set of boxes, how does the number of possible configurations of values in the observed boxes change with time? If those boxes went down to the level of individual particles and individual cells in the grid, they would all just say, well, there's only one thing here at this time. But if you coarse grain it, you find that you get indeed the tendency to, on average, gradually increase the entropy, the number of possible states of this coarse-grained system, and that's exactly what you would expect from the second law of thermodynamics. So this is showing that indeed this sort of second law behavior occurs even in these simple cellular automaton models, and you'll see the actual sort of increase of the entropy. Now, one of the questions is, okay, so what's really going on in a case like this? This is showing, this is showing from different initial conditions for a particular cellular automaton. This is showing sort of the approach to randomness in those different initial conditions. And it's showing that independent of the initial conditions, except for very, very special cases, you'll always tend to get this sort of randomization occur. In a sense, the force of complexity is sufficiently great that it will always overwhelm whatever it is that you tried to set up carefully in the initial conditions. And so now we have a better understanding of what's going on. And in fact, in the discussion that will come up in chapter 10 of NKS, we already have the sort of precursors of that. Kind of the point here is the fundamental reason that we see second law behavior is because we're, in a sense, doing computation that's sort of encrypting the initial data associated with this system to produce something where the final result is the result of intrinsic randomness generation, the things we talked about in chapter 7 about sort of the intrinsic generation of randomness generated like Rule 30 does it, like the digits of pi do it. That's what's happening in these systems. The reversibility business is kind of a sideshow. The important thing is computational irreducibility, the phenomenon that one is putting sort of, that there's computational work going on that's leading to behavior that we cannot readily decode. That in order to decode this behavior, we'd have to do sort of as much computational work as was done to create it. And so that's, in a sense, ultimately why we see apparent randomness, is that we as observers of this, we are computationally bounded observers of this. And that means, and we're not going in and looking at what each individual cell is doing. And so that means that we conclude that there is this thing where we're going to increasing randomness, where the entropy is increasing and so on. So I see that as being finally kind of a derivation of the second law of thermodynamics. This idea that the second law of thermodynamics is computational irreducibility in action, so to speak. Even though there is underlying reversibility, even though there is underlying, there might be a simple initial condition, a simple rule, the force of the phenomenon that NKS is really about, the force of computational irreducibility is strong enough that it can break out of the simplicity of the rules, the initial conditions, and so on, to produce something that it shows great complexity and great randomness. And that's why the second law of thermodynamics occurs. And we as observers of this are, again, not able to decode what's going on. And so it seems to show increased randomness, increased entropy, and so on. Okay, so that's kind of a story of why the second law works. And what we see is for different kinds of systems, there's more obvious second law behavior than others. I mean, in a sense, when we have a gas and we put a bunch of molecules in the gas and we put them in a box, maybe they start off in one corner of the box. It doesn't take very long before they sort of spread out across the box and they make this kind of completely random behavior in the box. But if we have a solid, then it's much less obvious that things are sort of randomizing quickly. And so it is with a bunch of these rules. There are rules which randomize quickly, and there are rules that kind of stay very, very solid, so to speak, and where there isn't that same kind of randomization. But the underlying phenomenon, if if it's left to go there, it will typically show computational irreducibility and will show the second law of behavior. Well, that's what usually happens. So one of the questions that I asked is, given that we now have a more fundamental understanding of the second law and the computational origin of the second law, is the second law always true? And here's a case where it isn't really quite so obviously true. This is rule 37R. And what happens in this rule is that there's, in a sense, an infinitely long transient. Yes, you start from a simple initial condition and things kind of tend to spread out, but for a very, very, very long time, not an infinite time, but a very long time, there's sort of, while the actual initial conditions aren't very visible, there's still a lot of structure in the system. It still is not typical of the ensemble of all possible behaviors. So this is a case where, even though normally the force of computational irreducibility combined with the fact that we as computationally bounded observers can't decode that, tends to lead us to just say second law is true, it's second law all the way. But what we're seeing in rule 37R is in effect this infinite transient where our powers of observation are successfully decoding some of what's going on, and there is and where it's not as obvious computational that there is computational irreducibility, but we successfully decode certain aspects of that to make us not show what would be normal second law behavior. I think there's a picture here of what happens. It's kind of interesting what happens with this small piece of kind of randomness in the middle here. What we're seeing is that actually, in a sense, we're seeing a simpler and simpler setup here. But in a sense, what's happening is a little bit like what happens in many physical systems. We're radiating the sort of information on this initial condition to infinity. It's like heat is coming off, radiative, there's radiation coming out, and the details of these particular localized structures encode what was there. Remember, this is a reversible rule. So it always should be the case. If we've ended up with something which is very, very trivial here, it better be the case that we've radiated away enough information that we could go back and reconstruct that initial condition if we needed to. And that's what's happening here. It's a very kind of physical version of what's going on. So I talk about the repetition periods of rule 37R, talking a little bit about the behavior of sort of this, in a sense, this avoiding of the second law, making the second law be something that necessarily takes a very long time to be relevant here. Okay, going over a few of the notes here, I talk a little bit about things like testing reversibility of cellular automata. Turns out in one dimension, there's a definite upper bound to how far you have to test, how big the blocks you have to test to guarantee reversibility. In two dimensions, that test becomes undecidable. And in general, it's like solving a tiling problem in two dimensions. It's not possible to get a finite description, a finite, that there's no upper bound that you can give on how much computational work you'll have to do to guarantee that this is a genuine reversible cellular automaton or not. Here I'm talking about cellular automata where there is an inverse rule, but the inverse rule may not be the same as the forward rule. And sometimes the inverse rule may actually have, for example, larger neighborhood size than the forward rule. Now, many times since the early 1980s, I have been interested in seeing whether one can make public key crypto systems based on this phenomenon of cellular automata, where the forward rule and the backward rule aren't of comparable complexity, so to speak. I've never succeeded in doing that, but I don't think it's necessarily impossible. And I kind of, that's a thing that's still out there as something to explore. Let's see, these are just specific properties of specific kinds of cellular automata. This is various kinds of details about rule 37R. this is talking about something that actually still needs more investigation. It'd be a good summer school project, actually. If somebody hasn't done it over the last 20 years, I don't remember. To look at reversible mobile automata, we can also have reversible Turing machines. I talk here about reversible multiware systems. Wow, those are things I've been studying just in the last couple of months. As usual, it's a footnote in the NKS book, and it emerges into a giant structure, a couple of decades later. But I'm talking here about other kinds of systems that can be made reversible. I talk here about time reversal invariance and the fact that it's not quite the same as reversibility. Time reversal invariance is known to be violated in the decay of the K0 particle in particle physics, and now also in the B system and some other places. But this is something of relevance now to our physics project of how is there approximate time reversal invariance, which is really just literally flipping the direction of the rewritings in our hypergraph, parity, which is a more complicated operation involving inverting the hypergraph, and charge conjugation, which is an operation that on the branchial graph, it's kind of an inversion of the branchial graph, and how all those operations come together to make CPT, which is a thing that appears to be a global invariance of quantum field theory guaranteed by kind of relativistic invariance. And that's a more complicated story, which actually should be investigated more in our models, because CPT invariance doesn't really hold quite in the presence of gravity, and we can kind of start to see why that is. Actually, that's a good idea in the context of our models. Okay. As is my won't here, there's I think a rather good kind of capsule history of thermodynamics and the emergence of the idea that heat is not a substance, is not a phlogiston, so to speak, and that heat is a property of molecules bouncing around rather than being a separate sort of fluid-like thing in a material. And that was a thing that kind of emerged in the early to mid 1800s. And the atoms, it became clearer and clearer that materials were made of atoms, and that allowed for different kinds of things to be what was going on in these systems. Talked about Maxwell and Boltzmann. Boltzmann was very big on this thing he called the H theorem, which purported to be a theorem that would mathematically prove that entropy increases. Entropy is minus H, basically. This was very confusing to people. What was going on is the Boltzmann's theorem comes out of the Boltzmann equation, which is an equation that describes collisions, let's say, between pairs of molecules leading to pairs of molecules going out. The thing was that there was sort of an implicit assumption made that the molecules were uncorrelated before they made each collision. But if they were uncorrelated before the collision, then after the collision, they're correlated because they just collided with each other. So you know that they have some properties that are sort of entangled between those two molecules. Well, the point is that that creates sort of a time asymmetry because you're saying they're uncorrelated before they collide, but they're not uncorrelated after they collide. So to really do the reversal, you have to reverse that story as well. And that's, although confusing, that's how things eventually work. Let's see, I'm just talking about different kinds of things that came out of the second law, and really the people were very confused about this. People have been very confused for a long time. What is the second law? Is the second law a law of nature? Is it a mathematical principle? Is it a definition of heat? What is it? And in the end, as we have this sort of computational understanding of the second law, we get to sort of untangle that and say the second law is a statement about us as observers and the interactions that we have with the necessary formal structure of systems and the phenomenon of computational irreducibility. So, for example, Maxwell, James Clerk Maxwell, had this idea of a Maxwell's demon that would be a molecule-scaled critter that would be able to sort of sort molecules and decide, open this door for a molecule, don't open it for that molecule, and so on. And he observed that if you had a molecule-scale critter, you would get behavior that could be quite different from the typical behavior that you would see in a gas. And that's kind of a statement that Maxwell's demon is kind of an example of an observer different from us as observers, but an observer that would lead to non-thermodynamic behavior. That with that kind of observer, you wouldn't conclude that thermodynamics works. With an observer like us, big compared to the molecules in a gas, bounded computational capability to decode what's happening in the gas, then you conclude there's second law behavior. Now, notice that things like Rule 37R are an example which actually we need to rethink about in the context of this kind of observer view, which we now understand better from our main physics project. But that's a case where we as observers are capable of observing features of that system. That system is still exposing features that we as observers can recognize, even though it's been run for a long time. And if we were to observe other features, we would say, oh, it's just random. But because of our visual system and other things that we're picking up, we actually, that system has features that don't appear to just become completely random. And that's sort of a case where with our particular powers of observation, we are kind of seeing something which is not thermodynamic behavior. That's kind of a way to understand that. But generically, thermodynamic behavior is a consequence of computational irreducibility, which is a consequence of the principle of computational equivalence. And it's kind of a story of how computationally bounded observers necessarily view the universe. Current thinking about the second law. Okay. There is confusion about why systems in nature have not all dissipated into complete randomness. Right, this is a thing. I used to argue about this with my friend Dick Feynman, who I have to say, I now understand why he was sort of, I think, definitively wrong about this, because he always used to be confused, as many physicists were, about if the second law says that things sort of degrade into the state of increasing randomness, why is it that the systems we see in nature have not dissipated into complete randomness? Why is it that there is actually perceived order in the universe? And the rather absurd claim is that there's order in the universe because it's just a fluctuation. If in the end, the universe will just produce something which is completely random. Now, in a sense, that's right, I suppose, now that I think about it a few decades later. In a sense, that's true, but it isn't what you think it is, in the sense that people talk about the heat death of the universe. Everything just turns into this situation where the whole universe is full of a gas where all the molecules are randomly bouncing around. And isn't that terrible? There's nothing left. But actually, there is something left. All those detailed molecules, or all those detailed motions of molecules, they encode tons of information. It's just for observers like us, that looks like it's completely random. But were we to be molecular scale observers, were we to be Maxwell's demons, we will be saying, oh, look, there is the trace of all of that amazing civilization from the 21st century or something, traced in the structure of these molecules and so on. Now, another kind of claim that's sometimes made is that gravity sort of violates the second law. I'm sure I talk about this in the NKS book because I've thought about that. I thought about that since the 1970s, and there's more to say about this. Okay, we're talking about biological systems and Maxwell's demon. I think the story of Maxwell's demon is really a story of the observer being computationally bounded and so on, more so than, for example, energy use by the demon and other such things. Oh, look at that. I predicted there'd be a section on self-gravitating systems, and there is. So yeah, I mentioned here that my original interest in cellular automata developed from trying to model the structure of self-gravitating systems for which they are actually rather inappropriate. But I talk about the fact that, wow, actually it's difficult to know what an idealized self-gravitating system would do. I mentioned here it's possible to do a small-scale experiment. Boy, I should have suggested that to people. I'd forgotten that was in there. That's an interesting thing to do, given that it's so easy to launch things into orbit now and get weightless conditions. It should be rather easy to do that. Huh. Interesting. Should try it. So anyway, I talk about what happens with galaxies and the way that gravity interacts with kind of the second law behavior. Let's not get into that particular discussion here. Cosmology, second law, the alignment of time in the universe, which I think we now understand quite well in our physics project, this recurrence phenomenon, talking about billiards, where you're really just having balls bouncing around a fixed region, and how that works. Okay, a little bit more detail about Rule 37R. Okay, now we're on to a new section. So the next section here is called Conserved Quantities and Continuum Phenomena. So the second law kind of suggests that what starts as perhaps very ordered will become more random. And that is kind of why we have things like fluids. A fluid has all those molecules in it, all arranged in, all sort of randomly arranged, and the aggregate of all those molecules will make this kind of continuum fluid behavior. When we have a solid, like a crystal, where all the atoms are lined up in some beautiful way, we don't have the same kind of phenomena that we have in fluids. So the thing that this section discusses is continuum phenomena and how those arise, how it comes to be the case that there are quantities which don't depend on the micro details of where each individual black and white pixel is, but is some kind of larger scale thing. And so here, we're just looking at, for particular cellular automaton rules, if we started off with, let's say, 25% black, these are rules that conserve the number of black cells. So here we're just shifting it. And here we have slightly more complicated behavior. This is Rule 194. But in any case, these are rules where the number of black cells is a conserved quantity. And now we're seeing here other examples where the number of black cells is conserved, but where the overall behavior is more complicated. There's a higher sort of force of computational irreducibility going on here, but yet we're conserving the number of black and white cells. And so here are other examples, I think, of conservation of cellular automata that have this conservation property. These are just cellular automata that are made in a slightly different way. Instead of being having 3 cells and producing 1 cell as output, they sort of have more obvious reversibility. And then these are cellular automata which are both, yes, this is what's happening on this page, which are both conserved things and are reversible. Actually, this one, I think this one is reversible, right? But doesn't conserve things yet. So, but the way this works is you have this collection of bricks, basically. You have 2 cells here going to 2 cells here. This is a block cellular automaton, and on successive steps, you're looking at the even and odd numbered bricks, so to speak, even and odd position bricks. Okay, so this allows us to have rules that are both reversible and conserve the number of cells. And so here we've got examples of that, and we're seeing that we in this case, we've got 25%, this case 75%, that fraction is preserved, even though the actual details of where the cells are may bounce around tremendously. Okay, so now what we're going to do, these are some rather nice pictures, I think, showing essentially second law type behavior with systems that are reversible, conserve the number of black cells, and show kind of computational irreducibility. So we're starting off from a simple configuration of cells in the center of the box here, and we're successively randomizing it, but always keeping a constant total number of black cells here. Same down here. So if we now ask the question, is that, how does that agree with sort of fluid behavior? We can say, well, imagine we had a gas where we had a higher density of gas molecules in the center of the box, lower density outside. What would that mean for the overall density of the gas? And we can try running it a bunch of times, and we can make an average of what is the average density. And what we'll find is that the average density shows this kind of diffusion behavior. It shows kind of just what we would expect from the continuum limit, the diffusion equation for these molecules. It's as if the molecules were just bouncing truly randomly around. In fact, they're not truly random. They're completely deterministic in the same way that Rule 30 is completely deterministic. But the kind of randomness they make, the intrinsic randomness they make, is good enough that for purposes of probing it by looking at overall density and so on, it appears to be completely random. It appears to show sort of increasing entropy, increasing randomization, and it can be modeled using mathematics, which just assumes that every behavior is random. And so in a sense, this is a case where we can derive the phenomenon of diffusion and so on. So this is deterministic underlying systems that show diffusion as their global behavior. So I talk a bunch about the general idea of conserved quantities. Here I'm just using black and white cells, but in physics there are many kinds of conserved quantities. You can talking about other kinds of conserved quantities here, other than just counting the number of black cells. You can count the number of certain kinds of blocks. You can do other kinds of things like that to find other kinds of conservation laws for cellular automata. Let's see. Okay, and there are conservation laws that are more local, more global, where the total number of black cells is conserved. There are ones where the local number of black cells is conserved. That's about block cellular automata. Yeah, one of the questions here is, when we've got an underlying cellular automaton and it's made of discrete cells, under what conditions can we say, oh, viewed on a large scale, it's just following the diffusion equation, or it's just following some particular partial differential equation? That's an interesting question. Most cellular automata do not have a limiting partial differential equation, I think. And most partial differential equations, there's no guarantee that there's a simple cellular automaton that limits to that partial differential equation, though it often seems that there is. But that's not something we know for sure, although it's the kind of thing that could potentially be determined. Okay, this is deriving the diffusion equation from these microscopic systems with assumptions about the fact that the intrinsic randomness generation is good enough to make something where we can take averages in the way that we could if it was just where we're sort of assuming randomness. The fact that some diffusion is kind of anomalous. Okay. All right. The next section. So that's a little bit on the origins of the second law of thermodynamics and of the origin of the concept of things like fluids. Okay, oops, wrong section here. So the next section in chapter 9 is sort of the bigger picture, ultimate models for the universe. And then I'm really going into the kinds of things that have become our physics project today. So I'm going to go over these a little bit more quickly because in a sense, we've got our whole physics project with thousands of pages of material that are really the expansion of this this section. There's altogether 70 pages in chapter 9 that's sort of expanded by some big factor as we really work through the details of the physics project. So I'm really going to talk about this more sort of at a historical level. Really what I'm talking about here is there an ultimate model for the universe? You might have thought, if you hadn't seen all of these phenomena of simple rules giving complicated behavior, you might say, look, the universe is really complicated. There's no way it can come from a simple rule. And if you say, well, maybe it's a program, but maybe it's a million-line program or a quadrillion-line program. Maybe it isn't a program that that is simple enough that we could like find it by just searching through all possible programs. But the whole point of the NKS book up to this point is look at the amazing fact that even rules, even very simple rules, even programs with very simple rules can show very complicated behavior. And sort of an extreme case of that would be our universe. Now, there are other features of having an ultimate model for the universe that is made from a simple rule, and I talk about some of those in this section. There's some sort of almost philosophical points, like, for example, if you have an ultimate rule that's a very, very simple rule, then you don't get to pack the features of the universe that we as observers at our scale and so on in the universe have commonly observed, even the fact that there are 3 dimensions of space, the fact that the muon exists and the electron and their mass ratio and all these different kinds of things. If you've just got one line of code that's supposed to be your rule for the whole universe, you don't get to put all those details into that one line of code. And so that means, among other things, that with these simple rules, you don't manage to pack those things in. All those have to emerge from the rules. If it's a simple rule, by the way, the distance between one rule and a sort of neighboring rule will be very large. So while one rule might lead to 3-dimensional space, the other might lead to 17.5 exponential dimensional space or some other such thing, dramatic differences, meaning that probably the amount of data we have currently in physics is probably enough to nail down, if we say it's going to be a really simple rule, to nail down, well, which simple rule is it? Okay, so I'm talking about those kinds of things, and the question of whether there are clues from the fact that current physics seems to have simple rules, simple laws that the particular laws that emerge are simple relative to other laws that could emerge, and how that works in the emergence of laws from something underneath, and so on. Talking about kind of the history of creating definite laws of physics, and the possibility that there is no ultimate simplest, that there is no ultimate law of physics, that it's sort of just you go further and further down, and there are more and more different laws as you go further and further down, and why that might be and why that might not be the case, and the fact that with the intuition that one has from the rest of the NKS book, it becomes much more plausible that there really is a bottom level to everything. Okay, so the next thing that I start to talk about is, okay, what is that bottom level? And I talk about the nature of space. And this is something which is really the big starting point for our physics project, and that was sort of seeded in the early 1990s in what became the NKS book. And I talk about the fact that space acts as a continuum down to 10 to the minus 20 meters. It's now, the limit is about 10 to the minus 22 meters. But maybe that's not right. Maybe space isn't a continuum. What might it be? And I talk about the fact that it's not a cellular automaton. It doesn't make, for many reasons, that is, a cellular automaton is already sort of prejudging too much about the structure of space. So, and I talk about how that might work. And then I start talking about networks, and I start talking about the idea of space as a network where the discrete points of space are just nodes in the network, and the network builds up as a kind of limit of the structure. Space builds up as kind of the limit of the structure of this network. And that's exactly the idea that launched our physics project today, is that space is a giant network, and that everything is made up from the properties of that giant network. And so that's what I talk about here. I point out that you can have many different, all that matters is the connectivity information of the nodes. You can render that's the same network rendered in many different ways. And then I talk about something which we've talked about a lot in the physics project. I talk about, okay, you can have this network, and depending on how it's connected up, it behaves like space in different numbers of dimensions. So what I did in the NKS book was I looked at the very simplest kinds of networks. I looked at trivalent networks, networks where every node is connected to exactly 3 others. 2 isn't enough, but 3 is. And if you have 4 nodes connected to a given node, you can always get that by having a pair of trivalent vertices. Okay, so in the NKS book, I considered what I thought of as being sort of the simplest networks, which are trivalent networks. Now, it turns out there are some sort of complexities of dealing with trivalent networks that I did address in the NKS book, but I never found them very satisfactory. I never found them very aesthetic. It's like saying, pick any number, oh, but by the way, it has to be prime type thing. And I wanted it to be the case that we could imagine picking sort of any possible rule. When I realized, I think in 2018, that one could use hypergraphs to do that, that was for me a very important sort of liberating moment that allowed the physics project to go forward, because I didn't have this kind of, oh, there are only certain rules that will work. We'll talk about why I thought that was the case for trivalent graphs later. But it turns out, in the end, now that we understand multi-way systems and so on in the physics project, we could have used trivalent graphs. In fact, even in the description of the physics project, the technical introduction of the physics project, I show how trivalent graphs are equivalent to the physics project as we have presented the physics project today. It's a little bit more natural to use hypergraphs, but it's equivalent to use trivalent graphs. So in a sense, the idea that's in chapter 9 here is exactly the idea that we now have, but we didn't have quite the context and details to fill in everything that we needed. But this is showing on this page, it's kind of like, depending on how you connect up the nodes, you get something which behaves like a 2-dimensional or 3-dimensional or infinite dimensional or curved 2-dimensional kind of system. And these are rather nice pictures. This is showing, starting from a given node in this graph, this is arranging this picture to be such that nodes a certain graph distance away are arranged progressively to the right here. And so this is explicitly sort of showing the growth rate of the number of nodes as you walk outwards from a given node in this particular graph. And that linear growth rate, you're doing one level of accumulation or integral or whatever, that growth rate shows this is a two-dimensional thing, this is a three-dimensional one, this is a two-dimensional one, but with curvature, which causes the growth rate of these balls that you grow to be slightly less than r squared. So this is stuff that is very much front and center in the beginning of our physics project now. It was already in the NKS book. I wrote this section probably in the early 1990s. This stuff I already knew. And I already knew that one could sort of get, I'm talking about this growth rate of the number of nodes and so on, that one could already get these kinds of things. Then I talk about, well, what might the actual network for the physical universe be like? Let's see, how do I talk about this here? Okay, so what I'm talking about then is space versus time. So one feature of the most obvious kind of way to do things in the NKS book is you've got a rule, you've got some initial condition for the rule, then you run the rule, and progressively through time, the rule produces different configurations. And so that would be a fine view of the universe based on our experience with time in the universe. But physics has kind of said for 100 years, no, actually space and time are the same kind of thing. So the first thing that I explore here is, well, what if space and time really were the same kind of thing? And instead of us making this network that represents space and having it progressively change through time, we say, let's make this giant crystal that is space-time, this giant structure that where the nodes in the structure represent essentially events in space-time. They don't represent the state of space. They represent sort of everything that happens in the whole history of the universe. So what I now did here was, you might remember from chapter 5, tilings, where we say we have a grid, a two-dimensional grid of black and white squares, and we're saying we want that grid to be such that at every position in the grid, we have certain constraints on what the neighboring black and white squares might be. Okay, this is a different idea. This is an idea where instead of having a grid, we just have a graph, and we say we want the graph to be such that at every node of the graph, the local region, the local neighborhood of the graph has this form. It has some hairs sticking out, but the local neighborhood looks like this. So the question is then, given a certain local neighborhood, what graphs are consistent with having that local neighborhood? Like in this case, you've got this self loop and it has one hair sticking out. The only graph that's consistent with that template is this graph here. And so similarly, we can go down here, like this weird graph here, the only graph consistent with it is that graph here. This graph here, the only graph consistent with it is the net of the dodecahedron shown here. So so this is kind of a straw model of the universe in which we're saying we just want it to be the case that in space-time, there's a certain sort of crystal structure to space-time where we just have these particular local neighborhoods defined. Now, I argue that this isn't a very good model for physics. This is an interesting mathematical system, which actually I don't think has been investigated much more than what's in the book here, and it's something that would be nice to investigate further. These are essentially vertex transitive graphs where you have the same structure at every vertex, and you're asking, what can you grow consistent with that? What are the kind of tilings that you can get, the graph tilings that you can get consistent with that local neighborhood structure? Okay, but I kind of give a bunch of arguments for why it probably isn't the case that space and time are the same in that sense. I'm going back here to some reversible cellular automata, which have the feature that for them, space and time, even at the level of a cellular automaton, you kind of can't tell which is the time direction and which is the space direction here. And it's kind of an interesting phenomenon, but I don't really believe in it. So now I start talking about time and causal networks. So this is again something that is very much has blossomed in the physics project, but was already there in the NKS book. The idea that, I talk about the fact that in a cellular automaton, if you were going to have that be a representation for time in the universe, you have to have a global clock that synchronizes everything in the universe. But what's the alternative to doing that? Well, what I talk about is something like a mobile automaton or a Turing machine, where there doesn't have to be a global clock because only one thing ever happens at a time in the universe. But what there is, so for example, we have this one active cell that's bouncing around in the universe. And we ask the question, well, that couldn't be our universe, could it? Where there's only one active cell bouncing around. Then we realize, no, actually, that argument isn't very good, because if we're observing a piece of the universe and we're saying, oh, nothing happened in that part of the universe because the active cell isn't there, we can't tell what happened until the active cell reaches us and updates us. So in other words, this very extreme idea of just one place is active at any moment in the universe, we can't necessarily distinguish that from what actually happens in the universe, because we can't know whether everything froze while we were being updated or we froze while everything was being updated and so on, because we can't tell what's happening except through essentially the causal relationship between us being updated and other things being updated. So, and this is a very much this is very much the story of the physics project. I mean, this is really very explicitly spelled out here in the NKS book, and kind of I'd almost forgotten about it actually, some of the details of this. But it's the exact same thing that we're doing in the physics project. This is the formation of a causal graph. And so this is saying, here's the underlying behavior. This is a mobile automaton. And now we're looking at these events. We happen to draw them in yellow when we're doing them in the physics project now. Here are the events that are these update events. Well, now let's gradually just look at how does each update event affect, how does the data that is the output from the update event, where does it get used in subsequent update events? And so what we're seeing here is just sort of the causal dependence of update event number one. Yes, one of its outputs is going to be used in event three. It's not, and then from three, we're going to be using it in four, and so on. And so then what we do is we can make a causal graph where the nodes of the causal graph are just the update events. And that's exactly what we do in the physics project. This was the first such causal graph being drawn here in the NKS book. And this thing that's interesting is this causal graph is really, in a sense, uniform in space-time. Even though at the beginning here, we just had this one active cell that's bouncing backwards and forwards in space, by the time we're drawing the causal graph, we've got something that is really, in a sense, uniformly laid out in space and time. Okay, so I talk about, I'm talking about the formation of causal graphs, and I say that we're going to look at some causal graphs here for different kinds of systems, and we're going to see different kinds of structures for these causal graphs, and this is just unbelievably similar to what we see now in the physics project. And although and the causal graph we're getting, well, in the physics project, we use as the simplest example, typically string rewriting systems. This can be seen as a string rewriting system, just where only one string is rewritten at a particular time. Okay, I guess I went to, I'm just looking at more examples of this phenomenon of the formation of causal graphs, and there are some details of, well, what kinds of things can happen in causal graphs that I discuss here. Let's see. Okay, 1D mobile automaton, which grows into an exponential dimensional causal graph. Just talking about that phenomenon. And what's this one? Okay, so this is now looking not at a mobile automaton, but instead at a system where there can be multiple rewrites, where there's not just one active cell that has to move around, but now where every time you see a black cell, you can rewrite it to this. This is a multi-way system. This is a string substitution system that we would now start talking about in terms of multi-way systems. In fact, I'd already talked about in chapter 5 in terms of multi-way systems. And so this is showing the same sort of derivation of the causal graph for this system, but now we, instead of having just one active cell, we say you can update this string according to any rules that apply, and this is showing how you get the causal graph from that. Okay, and this is more causal graphs with slightly different update. Oh, there are the update rules, and shown at the sort of smallest scale, kind of from outside the system. This is the causal graph shown for what you can tell from inside the system. Yet more causal graphs showing different kinds of behavior. This is sort of recapitulated in the physics project now, where we're again looking at causal graphs from string rewriting systems. This is kind of, that was the precursor to all of that. Okay, this is showing something which again we show now in the physics project, which is we show that you can reorder the underlying updates in certain cases for certain rules, and find that even though you've reordered the underlying updates, the causal graph of what depends on what event depends on what, is still the same. Sometimes that's the case, sometimes it's not the case. This is the phenomenon of causal invariance that I kind of came up with in the NKS book, and that again features prominently in the modern physics project. This is a sorting rule, one of our most common examples of a causal invariant system. That it doesn't matter. These are two different orders in which the underlying rewrites are done, but yet eventually the behavior is the same, and we'll find that the causal graph is also the same. And let's see, the second one. Yeah, okay. So this is also one where the causal graph is always the same. It's kind of a nice example, actually. Okay, and I'm now talking about under what circumstances you have causal invariance, that is, that the causal graph will be the same independent of the order in which you do the updates. And I'm pointing out that if you have certain non-overlap conditions for the left-hand sides of the string rewritings, that guarantees causal invariance. Okay, this is a big section: uniqueness and branching in time. This has to do with, well, if you've got these possible rewrites, and is there a unique history in time that you get from doing these rewrites? This is the thing that really, I think, I sort of evolved my point of view about this in the new physics project as compared to what was in the NKS book. In the NKS book, I was well aware of the fact that with these kinds of possible updates, you could get a multi-way graph of possible histories for the universe. But I argue here, well, it's actually kind of the same argument that we're now making in the physics project. Actually, this is, wow, this is really the same. Oh, well, I already knew this 25 years earlier. Pity that the world didn't encourage me to pursue this at the time. A lesson I have learned many times in my life, which is do what you think you should do, independent of any outside feedback to the contrary, so to speak. In any case, I say if one were to look at the multi-way system from the outside, the path, yeah, okay, so entities inside the multi-way system, our perception will inevitably be that a single path was followed corresponding to a single history. I would nuance that slightly today to talk about the fact that we conflate paths. We don't necessarily follow a single path. Okay, so I talk about the fact that we used to think that we had a unique position in space. The belief still exists that we have a unique history in time. If the universe is part of a multi-way system, that will not be true. And then I talk about the fact that at a human level, I find it disappointing to think that none of the details are unique. But what I probably say here, let's take a look if I say that, is that causal invariance kind of solves that problem. Let's see. I wonder whether I make that point here. Oh, yes, I'm about to make that point. Yes. I'm basically making the point that with causal invariance, it is no longer the case right. This is basically in words what we now are understanding in terms of causal invariance and the concept of the emergence of a single thread of history for our experience. I don't think I understood this. I think the words that I wrote here are maybe in 20 years, it kind of my recollection of what I had figured out dulled slightly, because I think actually the words that I'm saying here are very close to what we've now said in our physics project. Right. Means that the particular rules followed by the universe do in fact have the property that they always lead to the same causal network, I say here. That turns out to be guaranteed ultimately by this Rulliad object that studied in the last year or so, the Rullial multiway limit. I didn't know about any of that stuff when I wrote the NKS book. All right, continuing in the NKS book, the next thing I talk about is the evolution of networks. That's a huge deal in the physics project today. The physics project today is all about the evolution of hypergraphs. In the case of the NKS book, I was dealing with trivalent networks, and so I was interested in the evolution of trivalent networks. And you have these very elegant behaviors where a single node is turning into this triple of nodes, and you get this nice nested pattern and so on. And then I'm starting to look at the possible rewritings of clusters of nodes going to other clusters of nodes. And this is really the same story as in the physics project, except in the physics project, it's using hypergraphs. Here it's using trivalent graphs. It's a slightly more elegant setup with hypergraphs because there aren't these constraints on what the possible rules can be. Now, here I'm showing an actual evolution process where, I'm showing how, yes, I'm showing if you have a rewrite for this cluster of nodes, there are many possible ways that those rewrites can happen. This is the story of why it's a multi-way graph that gets generated rather than just a single history. Okay, well, here's our example of actual evolution of one of these networks through time. And this is using these particular rules here. This one here starts off from these tetrahedra or this thing, and this is the behavior we get. This was kind of difficult to make back in the day. I tried to visualize it. This is kind of a stack of these are the states of the system. We haven't actually made similar things for the physics project today, and perhaps we should, that show kind of the, that sort of show the thing, because the graph layout for these was a little bit more by hand done in those days. And the fact that this didn't sort of randomly flip around, that this node that becomes these nodes here are sort of under the same place as that node came from. That was kind of pseudo by hand arranged. And it will be much more difficult to do that for very large networks. But this is showing the evolution of the network under network rewriting, same as the modern physics project, but with trivalent networks here. And so these are examples of the evolution just starting from that sort of tetrahedron graph according to a particular rule. But remember, this is a particular rewriting sequence that is essentially one branch of the multi-way system. I guess these are some other examples of things getting more complicated here and getting pretty difficult to visualize what's going on. Okay, these are the causal graphs. So those are really the same story as with the physics project today. Those are the underlying spatial structure. This is the causal graph, the space-time structure, and this is showing the different kinds of causal graphs that you get from those different kinds of systems. Okay, we're talking here about what possible graphs can occur in the rules for rewriting trivalent graphs. Now, one advantage of hypergraphs is any old relation can be rewritten as any old other relation. In the case of trivalent graphs, there has to be an actual graph structure that you can rewrite, something that you can explicitly guarantee is trivalent. In the hypergraph case, you're not guaranteeing anything like that. It's just an arbitrary relation. So I view that as being a bit more elegant. But here, okay, so in order to get causal invariance, one way to guarantee to have causal invariance is to have no overlap between either for the thing you're rewriting to not be able to overlap itself or anything else you could be rewriting. That guarantees to have this order independence because you can't get sort of tangled up in these overlaps. So these are pictures of the simplest clusters, I call them the simplest rewriting regions that have no overlaps with themselves. Those are things which are candidates which will be causal invariant. Okay, so I then did a big hunt for systems that had these causal invariant rewritings, but which had non-trivial behavior. And back in the late 1990s, I didn't find much. And so that was one of the things that kind of put me off from this kind of approach, is I've got to do a bigger search, bigger computers, and so on, to search for cases that were causal invariant and yet had complicated behavior. Okay, so this was an important section, space, time, and relativity. So this was me realizing that once you're dealing with causal graphs and causal invariance, you necessarily have special relativity. There's a derivation of special relativity, which I thought was pretty non-trivial because people really hadn't seen a derivation of special relativity. It's just a feature of the universe according to the standard sort of Einstein argument from 1905. So here I'm talking about what we would now call foliations. These are the simultaneity surfaces being identified in a causal graph. This is showing for this particular rewriting that this corresponds to a particular foliation of the causal graph, just the same as we're talking about in the physics project today. And this is then talking about how these slices of space-time work. This is the very simple example, one we've used many times in recent times, of the sorting rule showing its causal graph, and then showing that in that causal graph, one has relativistic invariance. I think this is a bunch of words that basically say that. Okay, oh boy, I just wrote a piece about the concept of motion. Boy, I should have read this again. I just wrote a piece about the concept of motion just a couple of weeks ago now, and how that works in our modern project in physics. This is, I guess, talking about, well, it's actually talking about the concept of motion, which is, although in a slightly more specific way than I'm able to talk about it today. This is talking about Galilean invariance, the invariance of behavior with respect to moving observers, which is a little different than what I was talking about now. Talking about how one derives the standard result of time dilation, the standard time dilation factor in relativity. It's kind of a nice picture showing how you form these light cones, and then that gives you this, you're kind of using up kind of things bouncing backwards and forwards within this region. You have a choice of either letting that sort of move in space or move in time. And that's kind of the story of time dilation. We now have a much cleaner version of that story to tell. And this is showing that it's inevitable that in these causal graphs, when we have causal invariance, that we will get precisely the time dilation factors that relativity says we should get. And that's something, again, that we've redone in the new version of the physics project. And it's better, cleaner, more general derivation in that case. Okay, well, the next question is, we've got this idea of how space works and how relativity works. How do particles work? This is very similar to what I was just writing about a few weeks ago, talking about the emergence of particles as kind of these defects in the structure of space. And this is talking about an example I've used many times. If you have a rewriting rule that preserves planarity of a network, you have this sort of crossing of lines represents the possible way that non-planarity can occur. And if you have planarity preserving rewriting rules, you can't destroy that non-planarity. And so that's kind of like a stable particle going around in this network. Okay, so I'm talking about particles moving at different speeds and so on. Causal graphs, I should reread some of this stuff. I think we've superseded it all, but I think this was actually a very good run-up, and I'm kind of proud of the intuition that I have, even without knowing all of the technical details that we now know, that this intuition is more or less exactly on track. So let's take a look. Well, we've also got a lot of notes to these sections, so let's just take a little look at the notes to some of these sections. I talk about, lots of things here about space as a network, and I'm not going to go through all these notes, but a lot of stuff about the mathematics of things that we will come back again in the physics project today. A lot of details about how you make three-dimensional trivalent networks, things like this. There's a section on definitions of dimension. Wow. Okay, that's very modern, because the definition of dimension, what I think people are now calling Wolfram-Hausdorff dimensions, that's what was defined here as sort of the obvious way to define dimension in these network systems. Okay. Talking about, this is again something I've talked about again recently, Cayley graphs, that's in terms of these, what I'm calling network constraint systems, that are these cases where one has the sort of tiling made of a graph that has a bunch of identical components. Lots of discussion of that. Okay, this is looking at symmetric graphs, which are a case of that, and so on. Okay, let's see. There's usually lots of interesting, juicy things in the notes here. Oh, that's interesting. Oh, wow. I talk about Petri nets. These have just reappeared in our physics project just recently. And talk about the origin of flowcharts and causal networks and their origins here. Yeah, these are all things that have sort of reappeared in the physics project. Boy, this book has a lot of stuff in it, but I guess we all knew that. More about different kinds of causal graphs and generalized substitution systems and all kinds of things like that. That's kind of okay. Oh, I'm talking about what on earth did I say? Oh, I say the sequence of symbols I call strings have absolutely no direct connection to the continuous deformable 1D objects known as strings in string theory. Right. The ultimate pun joke is that maybe string theory actually is a limit of these string rewriting systems, but that's a different story here. Okay, I talk about distributed computing and its relationship. There's again something we're looking at again now. This has to do with synchronization in an otherwise non-synchronized system. Again, things we've been looking at in recent times. Many worlds interpretation of quantum mechanics, parallel universes, the notion of completion. That's something that, again, we've talked about recently. That's a big thing in our metamathematics investigation, is ideas about completions. Also something Jonathan Gorard has that as sort of a centerpiece of a view of quantum mechanics. Again, a discussion of that. There's a discussion of that, kind of a nice summary of it, I think, here in the NKS book. Network evolution. Okay, lots of stuff here about network evolution and graph grammars and so on. I gather that in the intervening years since the NKS book came out, there's been more study of graph rewriting, and the things that I made up in the NKS book for the ways to rewrite networks have a bunch of fancy names now. And let's see, I'm looking at here, oh gosh, all kinds of things. Connectedness of the universe. Boy, we talk about that again in the physics project today. Lots of different things here that to study. Talking about all sorts of different things about Space-like hypersurfaces, Cauchy surfaces, again, things that reappear in our physics project today. History of relativity and so on. Lots of stuff that, okay, this is the more detailed derivation of the sort of standard treatment of relativity. Again, all of the stuff can be kind of recapitulated in terms of our physics project today. I should explain one thing that kind of I got confused by back in the day here. When I was looking at network rewriting, one of the confusions was if you have a network with a low symmetry, with a high symmetry on the left-hand side, let me show you an example of that. So we've got something like, let me see, where is it here? Yeah, we've got something here where we say that's the left-hand side, okay? And it's got two tentacles. I don't know, where can we find one with two tentacles? Let's do a three-tentacle one. I don't seem to have a good example of that because I haven't got the simpler ones of those. But some of these, like that has a left-right symmetry to it. This doesn't have a left-right symmetry. So the question is, how could you rewrite from this to this? Because how would you know which of the different symmetry cases to bring in as the rewriting for this system here? Okay, so that was the thing I got confused by. The answer is go multi-way. This thing, it can be just as there might be many different places where that template would match on a graph. So similarly, there are many different ways that you can do the rewriting for different sort of choices of the symmetry of the right-hand side, different choices of which right-hand side you pick. Now, this is a thing that had confused me quite a bit when I was working on this in the 1990s. And now I know that confusion should have been a non-confusion. It's just like you've got multi-way systems with respect to the position in the graph that you're rewriting. You should also have a multi-way system with respect to which instance of the rewriting is the one that occurs. So that's a thing that I kind of missed in looking at this back in the 1990s, and it made me overly pessimistic about this kind of model. Oh, I forgot the elementary particles section here. And it's, oh, look at that. Oh, I forgot we had this. This is a nice example of a particle moving in a network. Particle that has a very caterpillar-like form that it's just this network gets rewritten to that, and that causes this sort of defect in the otherwise hexagonal lattice to move across the screen. Okay, let's take a quick look at the notes here. Notes for physicists. I don't know. That's probably realize that this works differently than traditional physics works. Okay, this is types of particles. Had the top quark been discovered? No, the top quark hadn't yet been discovered. We knew it was there, but it hadn't yet been discovered, and that's a typo because those shouldn't be V's; those should be news there. That's a typo in the online version. It won't be in the printed version. History of particles. Okay, that's interesting. Yeah, one of my favorite kind of theories that seemed like a bad theory, which turned out to be a good theory, is that atoms might be knotted vortices, might be knots in the ether, basically, that space would be pervaded by this luminiferous ether, as it was called in a very Victorian way, and that atoms, of which one knew there were a discrete number even in the mid-1800s, might be the different kinds of knots that you could make. Well, that idea as such isn't right, but this notion that there is a structure to space, kind of an ether that is the structure of space, that is very much right. And this idea that there are topological structures within that correspond to particles, that does seem to be right as well. So even though the original, it's knots in the ether, didn't turn out to be right, the spirit of that idea was indeed something very much along the right track. Okay, this is a discussion of detailed discussions about oh, wow. I forgot this. I've just been talking in recent times. You know, it's a funny thing. The idea that electrons are like black holes is an idea that I first wondered about when I was like, I don't know, 12, 13 years old. and first knew about black holes, which were just sort of becoming, and I think the term was coined in the early 60s, and then they were just sort of becoming more sort of recognized as real potential things. And the question was, could an electron just be a miniature version of a black hole? Okay, I don't know. In recent times now, as we think about the structure of particles in our physics project, that's very much a thing that's coming back is, the particles are like something like black holes, something like singularities in the structure of space-time, which aren't actually singularities, they're merely topologically stable structures in our network type model. And I noticed that at least an abstract correspondence between, for example, particles like electrons and gravitational configurations like black holes I mentioned here. So it's kind of amusing that was mentioned in the NKS book. Oh, and I talk about topological defects because I knew that was something relevant. This is about non-planar defects in planar graphs. And okay, this is talking about gauge invariance, which I didn't really understand yet in the context of these models in the NKS book, but we're slowly starting to understand it today. This is, well, that's interesting. Identifying particles and networks. This is a project I don't think we've ever really done, but it's a project that we're sort of getting ready to do for our full hypergraph systems today. Lovely, that's a knot theory with a bunch of knots. I think we had just introduced those in Wolfram Language and Mathematica right when the book came out. And so that I was able to make that picture. Talking about spin. Another thing we've talked about recently, talking about particle masses and the origin of particle masses. Talked about stuff I did in the late 70s about possible particle masses and so on. Okay, now we get to, we're getting towards the end of chapter 9 here. And towards the end of chapter 9, we have two sections. One is called the phenomenon of gravity, and the other is called quantum phenomena. The phenomenon of gravity is actually a quite strong section in the NKS book that really introduces what is a fundamental result of our physics project, the derivation of general relativity from network rewriting. The quantum phenomenon section is, I would say, less definite, more tenuous, and there were lots of things we didn't know when I wrote that, so I didn't know them when I wrote that section. So let's talk about the phenomenon of gravity. So I talk about the idea from general relativity that gravity is associated with curvature of space, and the idea that when you have shortest paths, GD6 in a space, if the space is curved, those GD6 can be deflected. And this is showing just some nice pictures of the flat, positive curvature, negative curvature, convergence of GD6 and positive curvature, divergence and negative curvature, the effect of having one sort of little dimple in this space-time and the attraction of the GD6 towards that thing. And this is kind of like the story of when you have mass producing a deformation in space-time, you get this kind of deflection of GD6. Okay, so now I talk about here the how do you measure curvature in one of these network models. And I knew at that time already that you could look at the growth rate of the total geodesic ball, and then you could ask what are the corrections to that. The corrections are given by the Ricci scalar curvature, and I knew that that was related to the Einstein equations. And what I basically argued here is that if you are going to have something where the large scale limit is well behaved, it is inevitable that you have to follow the Einstein equations, or at least the vacuum Einstein equations. I was not as clear I didn't know what energy was, and so I couldn't really do the Einstein equations have the form, the curvature terms on the left-hand side, r mu nu minus a half r g mu nu on the left-hand side equals 8 pi t mu nu. And t mu nu is the energy momentum tensor, and that's the thing where sort of energy is the source of curvature on the left. And I didn't know how to represent that energy in the universe back when I was working on this. So all I could look at was the left-hand side, and that being equal to 0. I correctly understood that that was associated with the fact that the growth rate of the volumes of the geodesic balls couldn't deviate too far from the thing that you would get from a pure object of a certain dimension. So let's see, I talked at length here about various aspects of gravity and the origin of the history of theories of gravity. This is about differential geometry. This is places where I was a little bit breaking down and having to use mathematical notation, although it was possible to use nice Wolfram language notation for the most important parts of this. Now that's the geodesic equation. Okay, those are examples of how one builds up networks that have a kind of buckyball networks that have a two-dimensional surface, but there's curvature in the two-dimensional surface. If it was all hexagons, it would be flat. If it was all pentagons, it would be curled all the way up into a dodecahedron, and if it has heptagons, it will curve outwards in negative curvature and so on. But this is a mixture of hexagons and pentagons, like a soccer ball. Hyperbolic networks, networks where everything's a heptagon or more, and where you can only put it together in such a way that it has negative curvature, and this is a particular way of projecting all those heptagons and so on into something that can be drawn in two dimensions. Okay, this is something that reappears in new physics project. This is the, well, this is just for a circle drawn on a sphere. This is the correction terms for its area. And this is the kind of general derivation down here of the Ricci scalar, the Ricci curvatures and so on. And this is a slightly more complicated formula, which we've been reusing and looking at higher order corrections to the Einstein equations in the physics project. Okay, this is the corresponding thing for cylinders, which we directly use in the physics project as part of the derivation of the Einstein equations. What is this? What is this? I don't remember what this is. Okay, this has to do with how you derive these continuum differential geometry type properties from this underlying kind of discrete system and how that limit process works. It's something we're studying more today, but this is the essence of it. And it's something actually we should look at what I wrote here, because there's probably quite a lot of interesting stuff there. Talking about manifolds and undecidability, that again is something relevant to us today. Okay, unlike in traditional differential geometry, my formulation of space as a network potentially allows concepts like curvature to be defined even outside of integer dimensions. Yes, that is absolutely correct. Very mathematically interesting. 25 years have gone by since I wrote that. We still don't know much about it. That's something we have to figure out for the physics project. It's something that will lead to a lot of interesting mathematics. Okay, this is more stuff about Lorentzian spacetimes. Torsion, something that's been studied by some people who've been involved with our project. This is causal set theory. Oh, I forgot I had this here. This is the what got named after this time, I think, causal set, the theory of causal sets. You just throw down events in space-time kind of at random, and then you build a causal graph based on the sort of random positions of those events in space and time. It was sort of a mystery how one ended up getting a particular configuration of events in space and time, where there's a built-in coordinate system for space and time that led to relativistic invariance. We now understand that on the basis of our models, and we can now use the mathematics of causal set theory to sort of build up above that. Okay, this is about the Einstein equations, and this is also about the question of what really should occur on the right-hand side of the Einstein equations. If you have the gravitational waves, are they part of the matter terms on the right-hand side of the equation, a source of gravity, or are they part of the left-hand side, the kind of the intrinsic curvature of space? And you can kind of move things around from one side to the other, and I talk a little bit about that here. But I didn't really know how energy would arise in these models, and so I wasn't able to kind of complete that. What's this about? Okay, yeah, this is about solutions to the Einstein equations. And boy, there's a lot of stuff here. This is about quantum gravity and the approaches that have been taken so far in quantum gravity. This is about spin networks. We finally understand now how spin networks relate to our models. They're basically limits of sort of ways of approximating kind of aggregated versions of our models, where instead of having just sort of unit length for every edge, instead of assuming unit length, you actually allow certain lengths for those edges, and then you have various consistency conditions for those lengths. And that's what leads to kind of the spin network formalism, which is kind of one can see as being an aggregated approximation to what we're looking at underneath. And oh boy, this is all kinds of very modern stuff about 6J symbols. All right, what's here? Cosmology. Okay, so again, I had an idea that this is again something very much comes up again in the new version of the physics project. The idea that the universe is not fixed dimensional, that that there can be a that the universe kind of started higher dimensional. And I already knew that these questions about cosmological homogeneity and so on that have required the whole sort of mechanism of inflation and so on to explain, you can explain those just by assuming that the universe started high dimensional or infinite dimensional and gradually cooling down. And that was something that I discussed in these few paragraphs here. What's this? Okay, now we're on to the final section of chapter 9. Which is, as I say, is probably the least satisfactory section of chapter 9. It's about quantum mechanics. And as you can see from these thumbnails, it's really just words. And it's a discussion of how one can think about quantum phenomena in the context of what we're talking about here. And I talk about the possibility that one can, in quantum mechanics, there are all sorts of things that seem to not be consistent with having a single thread of history in the universe. But I didn't really jump all the way to imagining that there are multiple threads of history in the universe and that we are seeing a conflation of those threads. I didn't jump to that in the NKS book. And that's one of the things that really opened up the physics project again 20 years later, was realizing that that was something that one should rethink. Now, I talk about vacuum fluctuations, the importance of the structure of space and the knitting together of space as vacuum fluctuations and so on. That's really all in here. But that's become much crisper in the physics project today. Let's see, what is this talking about? Okay, this is talking about measurement in quantum mechanics and the relationship between that and thermodynamics. Still relevant, although I think we have a clearer way of understanding the relationship of quantum mechanics. And I think the essence of it is something that I really didn't go for at least I don't think I did. I should reread what I actually said. It wasn't what I had kind of concluded from this. Was I was concluding that there was sort of this way of making a single thread of history and ending up with these sort of connections between different parts of space-time that could be associated with things that were not part of the sort of the overall structure of the network, but these sort of individual threads in the network. I think that might very well be a thing today, but it's not. There's sort of more structure that one needs before one gets to that. And that more structure is provided by this whole multi-computation idea, which is really a new emphasis relative to what I was doing in the NKS book. So, yeah, I'm talking here about distances on graphs and whether the way that works will be something that is just looking at whether distance is just looking at how far you have to go walking sort of from one node of the graph to another node of the graph, whether you have to be able to stuff a whole photon, a whole kind of topological structure through the graph, and the relationship between those two measures of distance. Okay, well, I talk about quantum theory and I talk about its history. Okay, this is a kind of an interesting page. This is sort of the page of what are the check boxes that you need to be able to check to say, yes, I've got quantum mechanics. because individual checkboxes here don't really cut it. It's the whole kind of formalism together that makes one feel that it's quantum mechanics. And sometimes people have thought, oh, if only you can get wave-particle duality, then you have quantum mechanics. It's not true. It's quantum mechanics is really a bundle of mathematical ideas, which we are seeing that we can get in the physics project today, but I didn't see how to get those things back 25 years ago. And we're sort of going down this list, checking off what we can get today. And this is kind of a historical list of what kinds of phenomena, ending with quantum computing. There is the potential for fundamental parallelism in computations. Okay, so this is kind of the inventory of what's in quantum mechanics, and there isn't really a single essence. It's really, you got to get the whole thing. Quantum phenomena, which things are easy to take in the large scale limit. Oh yeah, this is kind of a page that gets rediscovered regularly. This is just observing that you get essentially quantum behavior from a very simple sort of cellular automaton-like rule. And Dick Feynman observed this in the 40s. I think other people have observed it many times, that there's this very simple rule that gives you sort of the beginnings of something like the Dirac equation or the Klein-Gordon equation, which are relativistic wave equations. I don't think there's all that much significance to this. I think it's more just a coincidence of simple enough rules will lead to sort of the generic equations that one sees. I don't consider this particularly significant. Discussion about Feynman diagrams and their use as actual computation. We're not, the expectation is that as we move forward with our physics project and we understand more about what particles are, we will be able to get a version of Feynman diagrams that we can just basically deal with directly from the level of our underlying networks without something higher level, and we'll be able to just simulate those underlying networks to do computations in quantum field theory. This is a discussion of quantum field theory and the path integral, which we now think we understand on the basis of our physics project. I didn't see how to do that back in the days of the NKS book, talking about vacuum fluctuations, which I had worked on in physics also, and a little bit about how those might relate here. What's this? Quantum measurement. Okay. It's probably worth me rereading this now because, gosh, decoherence was already discussed in the 1930s. Well, yeah, I talk about sort of the origins of randomness in quantum phenomena. I had tried to make this randomness chip actually with Dick Feynman back in the early 80s, and we'd realized how hard that was, even on the basis of the supposed randomness in quantum mechanics. And in fact, this is a description of that issue of generating perfect randomness from quantum systems, and the fact that that's a difficult thing to define and to achieve because it's all tied up with how the measurements work. And the measurements, for the measuring device to sort of be back to a state where it can make another measurement, we have to sort of thermodynamically wait for things to happen. This is about Bell's inequalities. People always bring this up as one of the sort of the standards, whatever they call them, a flag of quantum mechanics, a very important sort of result of quantum mechanics. Now people talk a lot about Bell states and so on in quantum computing. This was just a description of those and trying to understand how that works. And let's see, is that the end of the notes for this section? I believe it is. So, okay, recapping. Chapter 9, that's what I've talked about today. Yes, one can apply kind of the concept of simple programs to fundamental physics. The first big win is the second law of thermodynamics, and understanding how that works and understanding the relationship between the second law of thermodynamics and computational irreducibility. Then back 25 years ago in writing the NKS book, I sort of poked at the problem of fundamental physics. I understood this idea of a network as being the fundamental structure of space, the concept that everything is made of space. the concept of causal graphs, the concept that causal graphs lead to relativistic invariance, the concept that you could get gravity and general relativity from structure of causal graphs and structure of network rewriting systems. All that I knew in the 1990s. And a lot of the technical underpinnings of our physics project existed in some seed form in the NKS book. I have to say that looking at this again, it makes me sort of all the more the fact that it took another 20 years before sort of the stars aligned to work on this project again is a bit of a disappointment. I did work on it a bit in 2003, 2004. I was still blocked by a few confusions that I had about symmetries of rewritings and the comparatively non-prevalence of causal invariance, things like this. That blocked me, plus the total lack of interest, I would say, of at that time, changed now, of kind of the theoretical physics community in these kinds of approaches, and the kind of no, we've got it, string theory is going to do it type thing. And the kind of a disappointment, considering that I had sort of grown up in that community maybe 15 years earlier, no, more than that, 20 years before that. It was sort of surprising to me that people were so locked in their ways by that time in physics that it's like, oh, a new approach? No, we don't need a new approach. So it took an extra 20 years. And despite the fact that I talked about these ideas in venues where millions of people saw it, just the very small number of people, I guess it only takes that small fluctuation. The people like Jonathan Gorard, who had seen the NKS book when he was in high school and had seen these things much earlier. It took only a few of those fluctuations to kind of seed, to nucleate what became our physics project in 2019 and 2020, and that's energetically continuing today. So it's I suppose that in a sense, almost, if all you were trying to do was to find a few young physicists who had sort of only just been born at the time when the NKS book came out, then perhaps the approach, or at least were very young when the NKS book came out, it's still worthwhile to kind of sow those seeds, because they can emerge decades later. And I feel like many of the things we're doing today, and I'm doing today, are things where the seeds are being sown, and it might be 50 or 100 years before those seeds actually take the kind of flower. So we can consider this video to be a sample of seed sown. I don't know when it will germinate, but I think that the general the sort of summing this up, chapter 9 has a lot of the raw material, which is now turning into our physics project, plus a bunch of stuff about thermodynamics and so on. And it's probably, at the time when the NKS book came out, it was the chapter that my friends in the physics community were most up in arms about. It's sort of, in a sense, it's a surprise in the history of these things that was something that people were, I think it got far enough to make people concerned. Not far enough as we've gotten now that one can really see how the story is going to end, and that we really have successfully nailed kind of the fundamental structure that we see in physics, which is something that I thought was probably going to be the case based on what had been built in chapter 9, but there were enough kind of things where I couldn't quite see my way through to the end that I wasn't completely confident of that it was a sort of an interesting approach, as what I said at the beginning of chapter 9, but not a look, we've nailed it type thing. All right, maybe I have time for a few questions, and then we should wrap up and move these questions perhaps to another live stream. Let's take a look at some of these. William asks, is measurement a time irreversible process? I think the answer is yes. That measurement is about taking all the details of a system and turning it into something which is understandable to us, that sort of fits into our way of thinking. And so it's kind of a thing where with our finite bounded brains, our computationally bounded capabilities, we're sort of taking all the details of the world and compressing them, sort of throwing away lots of those details to irreversibly lead to something which we can recognize. So I think yes. Okay, there's a question here from Waft about will the universe eventually reverse will it expand forever, or will it eventually reverse itself and go back to sort of the big crunch again? I don't think this is really addressing that particularly. Cosmological questions here. David is commenting about the monster group and standard model and so on. You know, there may be some great connection between things like the classification of finite groups and the possible rewriting systems. We don't know that yet. I think the next step is to understand how you can get things like rotational invariance, Lie groups, continuous groups out of network rewriting. We have indications of that, but we need to do more experiments and more mathematics to really see how that works. That's something I'm sort of hoping would be done by now, but we haven't gotten it done. I think it's something on my list. Waft is asking about multiple rules combined. Yeah, many of these systems, we are looking at two possible rewrites and seeing their combined effects. Comment from Universe Within about branchial space and complexity classes. I don't know. The whole story of complexity classes and computational complexity theory is really a story of the Roolead and of Rooleal space, which I didn't know about at all in the NKS book. I wondered about this. I wondered about, if we find a rule for the universe, why this rule and not another? I think maybe I had some discussion about that somewhere in the NKS book, but I wasn't happy with my answer. And the true story seems to be this Roolead story, which is a story that I just didn't really see coming in the NKS book. William is asking about half-integer spin particles and spinners and the spinner representations of the rotation group and so on. That is something which better come out sort of in the wash as we see how our hypergraphs both limit to the structure of space and limit to the internal symmetries associated with particles like spin and so on. Okay, so my guess is, and we had some indications of this a year or so ago, of how one can get spinners versus vectors in the limit of sort of transformations on these hypergraphs. I think there's arguably the sort of the fundamental idea of fermions has to do with sort of paths that branch versus the fundamental idea of bosons of paths that merge. And that may be closely related to what happens when one tries to sort of map one instance of the hypergraph into another one with a transformation, and this whole question about whether that is something that where when you sort of move by 360 degrees, whether you get back to what you started from or minus what you started from. And that's the question of whether you are dealing with an integer spin or fractional spin object or representation of the generalization of the rotation group that arises in models of space-time, et cetera, et cetera, et cetera. There's a fair amount of technical detail there from sort of the physics that's grown up in the last 100 years. But I think we don't quite yet know enough to be able to address this for our physics project, but we're definitely getting there. And that's one of the next upcoming projects is really to explore that in more detail. All right, well, looks like that's the end of the questions that I think I can immediately answer here. And Thanks for joining me. And next week, we will be exploring chapter 10 of the NKS book, which is about processes of perception and analysis. You know, it's funny, the NKS book just has an awful lot of stuff in it. And as we're coming now to study observer theory in connection with our physics project and the generalizations of our physics project, that's really a chapter 10 story about processes of perception and analysis. And I'll look forward to going through that in a bit more detail in another episode here, as we see it as sort of the on-ramp to the study of observer theory today. And I do want to say again that it's very striking to me. It's very, very nice that, you know, I put a lot of work into the NKS book, and the things that are there are surprisingly kind of permanent. And 20 years later, they still have sort of the same definitiveness that they had at that time. The only thing that I would add is multi-computation, multi-way systems, the whole development along those lines that's led us to such a fertile direction. In a sense, I view the NKS book as an important piece of the emergence of the computational paradigm for thinking about science. What we've got now is a generalization of that to the multi-computational paradigm. The computational paradigm is all about individual computations, individual rules, and what they do. The multi-computational paradigm is about the interactions between computations and the aggregate behaviors observed by observers to those interactions between multiple computations. And so that's sort of in that 20-year span, that's kind of the new thing that's emerged now that goes beyond the story that we had in NKS. All right, I should wrap up here. Thanks for joining me, and look forward to seeing you on another live